In mathematics, a function is a relation between a set of inputs and a set of permissible outputs with the property that each input is related to exactly one output. An example is the function that relates each real number x to its square x2. The output of a function f corresponding to an input x is denoted by f. In this example, if the input is -3, then the output is 9, and we may write f equals 9. Likewise, if the input is 3, then the output is also 9, and we may write f equals 9. The input variable is sometimes referred to as the argument of the function. Functions of various kinds are the central objects of investigation in most fields of modern mathematics. There are many ways to describe or represent a function. Some functions may be defined by a formula or algorithm that tells how to compute the output for a given input. Others are given by a picture, called the graph of the function. In science, functions are sometimes defined by a table that gives the outputs for selected inputs. A function could be described implicitly, for example as the inverse to another function or as a solution of a differential equation. The input and output of a function can be expressed as an ordered pair, ordered so that the first element is the input, and the second is the output. In the example above, f equals x2, we have the ordered pair. If both input and output are real numbers, this ordered pair can be viewed as the Cartesian coordinates of a point on the graph of the function. In modern mathematics, a function is defined by its set of inputs, called the domain, a set containing the set of outputs, and possibly additional elements, as members, called its codomain, and the set of all input-output pairs, called its graph. Sometimes the codomain is called the function's range, but more commonly the word range is used to mean, instead, specifically the set of outputs. For example, we could define a function using the rule f equals x2 by saying that the domain and codomain are the real numbers, and that the graph consists of all pairs of real numbers. The image of this function is the set of non-negative real numbers. Collections of functions with the same domain and the same codomain are called function spaces, the properties of which are studied in such mathematical disciplines as real analysis, complex analysis, and functional analysis. In analogy with arithmetic, it is possible to define addition, subtraction, multiplication, and division of functions, in those cases where the output is a number. Another important operation defined on functions is function composition, where the output from one function becomes the input to another function. Introduction and examples. For an example of a function, let X be the set consisting of 4 shapes: a red triangle, a yellow rectangle, a green hexagon, and a red square, and let Y be the set consisting of 5 colors: red, blue, green, pink, and yellow. Linking each shape to its color is a function from X to Y. Each shape is linked to a color, and each shape is linked, or mapped, to exactly one color. There is no shape that lacks a color and no shape that has 2 or more colors. This function will be referred to as the color of the shape function. The input to a function is called the argument and the output is called the value. The set of all permitted inputs to a given function is called the domain of the function, while the set of permissible outputs is called the codomain. Thus, the domain of the color of the shape function is the set of the 4 shapes, and the codomain consists of the 5 colors. The concept of a function does not require that every possible output is the value of some argument, e.g., the color blue is not the color of any of the 4 shapes in X. A second example of a function is the following. The domain is chosen to be the set of natural numbers, and the codomain is the set of integers. The function associates to any natural number n the number 4 minus n. For example, to 1 it associates 3 and to 10 it associates -6. A third example of a function has the set of polygons as domain and the set of natural numbers as codomain. The function associates a polygon with its number of vertices. For example, a triangle is associated with the number 3, a square with the number 4, and so on. The term range is sometimes used either for the codomain or for the set of all the actual values a function has. Definition. In order to avoid the use of the informally defined concepts of rules and associates, the above intuitive explanation of functions is completed with a formal definition. This definition relies on the notion of the Cartesian product. The Cartesian product of two sets x and y is the set of all ordered pairs, written, where x is an element of x and y is an element of y. The x and the y are called the components of the ordered pair. The Cartesian product of x and y is denoted by x times y. A function f from x to y is a subset of the Cartesian product x times y subject to the following condition. Every element of x is the first component of one and only one ordered pair in the subset. In other words, for every x in X there is exactly one element y such that the ordered pair is contained in the subset defining the function f. This formal definition is a precise rendition of the idea that to each x is associated an element y of y, namely the uniquely specified element y with the property just mentioned. Considering the color of the shape function above, the set X is the domain consisting of the four shapes, while Y is the codomain consisting of 5 colors. There are 20 possible ordered pairs, one of which is. Thus, the pair is in the function, but the pair is not. Notation. For more details on this topic, see functional notation. A function f with domain x and codomain y is commonly denoted by or. In this context, the elements of x are called arguments of f. For each argument x, the corresponding unique y in the codomain is called the function value at x or the image of x under f. It is written as f. One says that f associates y with x or maps x to y. This is abbreviated by a general function is often denoted by f. Special functions have names. For example, the signum function is denoted by sgn. Given a real number x, its image under the signum function is then written as sgn. Here, the argument is denoted by the symbol x, but different symbols may be used in other contexts. For example, in physics, the velocity of some body, depending on the time, is denoted v. The parentheses around the argument may be omitted when there is little chance of confusion, thus, sin x. This is known as prefix notation. In order to denote a specific function, the notation is used. For example, the above function reads the first part can be read as f is a function from to z, or f is a z-valued function of an valued variable. The second part is read x maps to 4 minus x. In other words, this function has the natural numbers as domain, the integers as codomain. Strictly speaking, a function is properly defined only when the domain and codomain are specified. For example, the formula f equals 4 minus x alone is not a properly defined function. Moreover, the function is not considered the same function, even though the formulas defining f and g agree, and similarly with the different codomain. Despite that, many authors drop the specification of the domain and codomain, especially if these are clear from the context. So in this example many just write f equals 4 minus x. Sometimes, the maximal possible domain is also understood implicitly. A formula such as may mean that the domain of f is the set of real numbers x where the square root is defined. To define a function, sometimes a dot notation is used in order to emphasize the functional nature of an expression without assigning a special symbol to the variable. For instance, stands for the function, stands for the integral function, and so on. Specifying a function. A function can be defined by any mathematical condition relating each argument to the corresponding output value. If the domain is finite, a function f may be defined by simply tabulating all the arguments x and their corresponding function values f. More commonly, a function is defined by a formula, or an algorithm, a recipe that tells how to compute the value of f given any x in the domain. There are many other ways of defining functions. Examples include piecewise definitions, induction or recursion, algebraic or analytic closure, limits, analytic continuation, infinite series, and as solutions to integral and differential equations. The lambda calculus provides a powerful and flexible syntax for defining and combining functions of several variables. In advanced mathematics, some functions exist because of an axiom, such as the axiom of choice. A graph of a function is its set of ordered pairs f. This is an abstraction of the idea of a graph as a picture showing the function plotted on a pair of coordinate axes. For example, the point above 3 on the horizontal axis and to the right of 9 on the vertical axis lies on the graph of y equals x2. Formulas and algorithms. Different formulas or algorithms may describe the same function. For instance, f equals is exactly the same function as f equals x2 minus 1. Furthermore, a function need not be described by a formula, expression, or algorithm, nor need it deal with numbers at all. The domain and codomain of a function may be arbitrary sets. One example of a function that acts on non-numeric inputs takes English words as inputs and returns the first letter of the input word as output. As an example, the factorial function is defined on the non-negative integers and produces a non-negative integer. It is defined by the following inductive algorithm. 0 is defined to be 1, and n is defined to be n. For all positive integers n, the factorial function is denoted with the exclamation mark after the variable. Computability functions that send integers to integers, or finite strings to finite strings, can sometimes be defined by an algorithm, which gives a precise description of a set of steps for computing the output of the function from its input. Functions definable by an algorithm are called computable functions. For example, the Euclidean algorithm gives a precise process to compute the greatest common divisor of two positive integers. Many of the functions studied in the context of number theory are computable. Fundamental results of computability theory show that there are functions that can be precisely defined but are not computable. Moreover, in the sense of cardinality, almost all functions from the integers to integers are not computable. The number of computable functions from integers to integers is countable, because the number of possible algorithms is. The number of all functions from integers to integers is higher, the same as the cardinality of the real numbers. Thus most functions from integers to integers are not computable. Specific examples of uncomputable functions are known, including the busy beaver function and functions related to the halting problem and other undecidable problems. Basic properties. There are a number of general basic properties and notions. In this section, f is a function with domain x and codomain y. Image and pre-image. If A is any subset of the domain x, then f is the subset of the codomain y consisting of all images of elements of A. We say the f is the image of A under f. The image of f is given by f. On the other hand, the inverse image of a subset B of the codomain y under a function f is the subset of the domain x defined by so, for example, the pre-image of 4, 9 under the squaring function is the set -3, -2, 2, 3. The term range usually refers to the image, but sometimes it refers to the codomain. By definition of a function, the image of an element x of the domain is always a single element y of the codomain. Conversely, though, the pre-image of a singleton set may in general contain any number of elements. For example, if f equals 7, then the pre-image of 5 is the empty set but the pre-image of 7 is the entire domain. It is customary to write f-1 instead of f-1, i.e., this set is sometimes called the fiber of B under f. Use of f to denote the image of a subset AX is consistent so long as no subset of the domain is also an element of the domain. In some fields it is convenient or even necessary to distinguish the two concepts. The customary notation is fa for the set f. xa. Likewise, some authors use square brackets to avoid confusion between the inverse image and the inverse function. Thus they would write f-1b and f-1b for the pre-image of a set and a singleton. Injective and surjective functions. A function is called injective if f for any two different elements are and b of the domain. It is called surjective if f equals y. That is, it is surjective if for every element y in the codomain there is an x in the domain such that f equals y. Finally, f is called bijective if it is both injective and surjective. This nomenclature was introduced by the Wvbailey group. The above color of the shape function is not injective, since two distinct shapes are assigned the same value. Moreover, it is not surjective, since the image of the function contains only 3, but not all 5 colors in the codomain. Function composition. The function composition of two functions takes the output of one function as the input of a second one. More specifically, the composition of f with a function g. Yz is the function defined by that is. The value of x is obtained by first applying f to x to obtain y equals f and then applying g to y to obtain z equals g. In the notation, the function on the right, f, acts first and the function on the left, g, acts second, reversing English reading order. The notation can be memorized by reading the notation as g of f or g after f. The composition is only defined when the codomain of f is the domain of g. Assuming that, the composition in the opposite order need not be defined. Even if it is, i.e., if the codomain of f is the codomain of g, it is not in general true that is, the order of the composition is important. For example, suppose f equals x2 and g equals x plus 1. Then g equals x2 plus 1, while f equals 2, which is x2 plus 2x plus 1, a different function. A composite function g can be visualized as the combination of two machines. The first takes input x and outputs f. The second takes f and outputs g. A concrete example of a function composition. Another composition. For example, we have here equals hash. Identity function. The unique function over a set X that maps each element to itself is called the identity function for X, and typically denoted by IDX. Each set has its own identity function, so the subscript cannot be omitted unless the set can be inferred from context. Under composition, an identity function is neutral. If f is any function from x to y, then restrictions and extensions. Informally, a restriction of a function f is the result of trimming its domain. More precisely, if S is any subset of x, the restriction of f to S is the function f, S from S to y such that f, S equals f for all S in S. If G is a restriction of f, then it is said that f is an extension of G. The overriding of f, xy by G. Wy is an extension of G denoted as y. Its graph is the set theoretical union of the graphs G and f, x, w. Thus, it relates any element of the domain of G to its image under G, and any other element of the domain of f to its image under f. Overriding is an associative operation. It has the empty function as an identity element. If f, x, w and g, x, w are pointwise equal, then the union of f and g is defined and is equal to their overriding union. This definition agrees with the definition of union for binary relations. Inverse function. An inverse function for f, denoted by f-1, is a function in the opposite direction, from y to x, satisfying that is, the two possible compositions of f and f-1 need to be the respective identity maps of x and y. As a simple example, if f converts a temperature in degrees Celsius C to degrees Fahrenheit f, the function converting degrees Fahrenheit to degrees Celsius would be a suitable f-1. Such an inverse function exists if and only if f is bijective. In this case, f is called invertible. The notation and f-1 are akin to multiplication and reciprocal notation. With this analogy, identity functions are like the multiplicative identity, 1, and inverse functions are like reciprocals. Types of functions. Real-valued functions. A real-valued function f is one whose codomain is the set of real numbers, or a subset thereof, if, in addition, the domain is also a subset of the rails. F is a real-valued function of a real variable. The study of such functions is called real analysis. Real-valued functions enjoy so-called pointwise operations. That is, give on two functions f, x, y, where y is a subset of the rails, their sum f plus g and product f g are functions with the same domain and codomain. They are defined by the formulas. In a similar vein, complex analysis studies functions whose domain and codomain are both the set of complex numbers. In most situations, the domain and codomain are understood from context, and only the relationship between the input and output is given. But if, then in real variables the domain is limited to non-negative numbers. The following table contains a few particularly important types of real-valued functions. Further types of functions. There are many other special classes of functions that are important to particular branches of mathematics or particular applications. Here is a partial list: differentiable, integrable, polynomial, rational, algebraic, transcendental, odd or even, convex, monotonic, holomorphic, meromorphic, entire, vector-valued, computable,